So, and the title of today's talk is Computationally Efficient Navigation in Dynamic Environments. So please, Albin, the floor is yours.
Yeah, thank you for those words. I will talk about this problem here I've worked with during the second half of my PhD period, namely planning robot motion from point A to point B in an environment with moving obstacles. So, and especially I've focused on how to avoid being trapped in local attracting points, like this poor robot here, trying to reach the desirable coffee and avoiding being trapped in the narrow passage between the human and the wall. So to give a quick background on what I've done, I will just start giving a brief overlook on the work for my first PhD period, and I will then go into the topic of today, robot navigation in dynamic environments. And after introducing in what context I have addressed the problem, I will present how to online make obstacle descriptions to reduce the risk of being trapped in local attractor points. And then in terms of potential field methods. And finally, I will present a model predictive scheme, which embeds both this obstacle modeling and the potential field approach. So the first half of my PhD, I was part of a project for automating waste disposal systems, and my work was together with the company Hiab to automate a truck-mounted crane for garbage collection. Aside from all practical problems it brought me working with, this led me into working with dynamical movement primitives, or DMPs. And this is a popular framework for programming by demonstration, which quite neatly encodes the demonstrated trajectory as a dynamical system, and specifically motivated by this slow crane, I focused on how to deal with limited velocity and accelerations. And later, this method has also been generalized to any trajectory generation scheme which is encoded as dynamical system, like potential field methods. So it can be combined with the topic I will talk about today as well. But in the second part of my PhD, I've been involved in a project aiming at introducing autonomous transport robots, or ATRs, in the Volvo Trucks production line. The ATRs are allowed to move freely in the area and are not restricted to some predetermined grid of paths to enable a more flexible manufacturing process. The setup is basically a fleet of ATRs which receive information about the current factory scene by cameras mounted in the ceiling. And given a range of tasks, for instance, deliver tool A to station 1, a global planner computes an optimal plan for the fleet. And this is done in the static map of the factory floor. So each robot gets information of when to be where. And given this information, each robot must then compute a control input to reach the waypoints while avoiding obstacles, where any dynamic obstacle identified by the cameras, like humans or manually driven forklifts, are now also taken into account. And it is this part which I have been focusing on. So basically computing the control input to move the robot towards next waypoint while avoiding all obstacles. And since this is done online, it should be done in within some specified sampling time. Right, so initially the local planning was made using a typical model adaptive control scheme for collision avoidance, where the collision avoidance is encoded as a constraint with no-go zones for the robot based on the obstacle geometries. And this works fine in many cases, but in some situations, the robot may get stuck due to the local nature of the MPC, like depending on the horizon of the MPC and cost function selection, the optimal solution might be to do a full stop before reaching the goal. And this is specifically if a sufficiently large region around the robot or is occupied, like when obstacles intersect. So in this case, we don't fully utilize the flexibility introduced by allowing movement on the entire floor. And depending on the shapes of the obstacles, the collision avoidance constraint may also lead to increased compute time to find the solution. Alternative strategies for collision avoidance are based on potential fields. Which is quite a mature strategy, where we basically have the an attractor point with the which is illustrated as a valley here, and all obstacles are illustrated as hills, and the combination of these two potential fields then results in a potential field, and the robot movement can be decided by the gradient descent of this resulting potential. These methods are very computationally efficient due to their closed form nature. And in contrast to the local nature of the MPC, there exists potential field methods which offer global convergence. But the convergence property typically is based on the assumption that the robot is operating in a star world. Star world, we have a star world if all obstacles are star-shaped and disjoint. So an obstacle is star-shaped if there exists a point in the set such that the line segment to any other point is contained by the set. And this could be seen as a generalization of convex sets, where this condition must hold for all points in the set and not just one. So obviously all convex sets are star-shaped, but we also see here in the middle an example of a star-shaped polygon, which is star-shaped with respect to this red point. And to the right, we see an example of figure which is not star-shaped, since we cannot find a point which fulfills this condition. But since without being too conservative, we can decide to model all obstacles as, for instance, ellipses and star-shaped polygons. This is not very problematic by itself, but with the second condition, that all obstacles must be disjoint, we come back to the problem of being trapped in local optima in scenarios of intersecting obstacles. So, and trying to solve the issue by just simply combining them into one, the intersecting obstacles, results in violating the first condition of star-shapedness. So this led me into formulating the following problem. Basically, that if we have a set of possibly intersecting obstacles, a robot position and a goal position, we want to create a new set of obstacles which are both disjoint and star-shaped. And that is that they form a star world. The new obstacles should fully cover the original ones, and neither the robot position nor goal position should be within the created set. And this should also be done in an online fashion. If we now can find such a O star, the potential field can be applied with respect to these new obstacles, so that the robot can safely navigate to the goal, and where we have the convergence guarantees, since we are operating in star world. Right now, so to solve this problem, I worked a bit on the zero star-shaped hull, which is at the core of the algorithm we've developed. And similar to convex hull, the star-shaped hull is the smallest star shape which covers it, the set. However, in contrast to the convex hull, the star-shaped hull is not unique for the set, but this depends on with respect to which point it is generated. So, for instance, if we take this non-star-shaped polygon again, and generate the hull at some point here, the green point, we get this extension in the red area, resulting in a star-shaped set. If we instead generate the hull with respect to another point, we get a different shape. So we can make use of this flexibility if we want to exclude some points like the robot position. And we can then actually compute all the possible points where we can generate the hull while still excluding the robot and goal position. And we call this the admissible kernel. So these are the key parts of the developed method to solve the problem of creating star worlds. And in essence, the algorithm consists of 3 steps. So first, we create clusters of all intersecting obstacles. Next, for each cluster, we find the admissible kernel. And finally, we generate the star-shaped hull for each cluster. And these are now treated as single obstacles. So in this example, instead of having 10, I think, obstacles, we will have 5 star-shaped obstacles. And when applying the potential field methods in this new star world, the trajectory converges to the goal, which can be converted to when operating in the original world, where we have these local optima traps. So looking at some examples with the moving obstacles, we see how they get combined and extended to form star-shaped at each time instant. But a simple approach, just applying the control input according to the potential field, does not directly take system constraint into account, or allows us to formulate desired behaviors like smooth changes in the control input. So to formulate such preferences is easily done in terms of cost function and constraints in an MPC problem. And so we have embedded this obstacle transformation and the guiding vector field in an MPC framework, allowing us to formulate these desired behaviors. And this is the next part of our work here. So where the motion control scheme is divided into 3 main components, where the star world generation and potential field constitutes the first 2 steps. So first, going through the scheme step by step, we first look into the obstacle transformation, where we first inflate the obstacles. So looking at the figure to the right, we take all original obstacles and just expand them with some clearance distance rho. Next, a star world is created based on these inflated obstacles using the algorithm I just presented. And in this star world, we have a potential field, use a potential field so that we have guaranteed convergence towards the goal. And we follow some steps along this from the current robot position to generate a target path. And the length of this path corresponds to the maximal achievable movement by the robot in the empathy horizon to get along enough distance. So when we have this target path, we solve an MPC problem to compute a valid control input sequence, resulting in a smooth robot path, which follows the target sufficiently close. And here, instead of including the obstacles in the optimization problem, we simply need a constraints on the tracking error. This ensures a collision-free movement since the target path is at closest at the distance rho from any obstacle. And as long as the MPC solution results in forward motion along the target, we converge towards the goal since the target is generated in this star world. So replacing the obstacle-based collision avoidance constraint with a tracking error constraint also enables a faster compute time for the solver. At the current stage, we have only implemented the planner in simulation environments, but hopefully the method can be evaluated in the experimental plant at Volvo Trucks factory during next year. Looking into some directions to extend the developed method, where all improvements, I believe, is quite low-hanging fruit, and I hope to be able to do this, at least some of them, during my final year. So currently, in the star generation, the robot workspace is assumed to be fully Euclidean space. And in many scenarios, this is not the case, for instance, for robots operating in a closed room. And an extension of the method to also consider boundaries would be beneficial. Next, so if predictions on future obstacle poses are available, it would be desirable to also adapt the planned trajectory based on these predictions, so that we actually make use of all the information available. And finally, up until now, we have only considered 2D scenarios, but all the developed submodules support 3D implementation, and it should, in theory, be quite straightforward to apply the motion scheme in 3D to actually investigate if this is applicable in practice, like in terms of computational effort and so on, could be of interest. And the scheme could then be used, for example, to plan motions for UAVs. This was all I had for this talk, and thank you for listening, and please feel free to contact me if you have any questions or something that you want to discuss.